సార్ వచ్చింది సార్. ఇమ్మంటారా?
షేర్ చేసింది. షేర్ అయిందా? మనం కొద్దిగా షేర్ అయిందా? ఎంతకెళ్ళింది? ఎస్కేప్
Sir, namaste sir. Sir, please unmute your voice, sir. Murthy garu, namaste andi.
నమస్తే సార్. నమస్తే అండి.
So
నమస్తే సార్ ఆచార్య గారు.
Sir, we will start the program sharply at 3 o'clock, sir, within 2 minutes.
Sure, sir.
Introduction.
Balai sir?
Sir.
We will start the program sharply at 3 o'clock.
Yes, sir. Good evening to all participants. On the occasion of 137th birth anniversary celebrations of Sri Srinivasa Ramanujan, our department is conducting a 1-week online international workshop on mathematics, bridging ideas and innovations MBII 2024 from 16th to 21st 2024. On the first day, that is 16th December 2024, Dr. L. Jagannathan sir, Professor, School of Computer Science and Engineering, Vellore Institute of Technology, Chennai, delivered a talk on mathematics of machine learning. On the second day, that is 17th December 2024, Sri NVRD Kumar Garu, Senior Faculty, Department of General Education, Skyline University College, Sharjah, United Arab Emirates, delivered a talk on lifelong learning in the era of AI. More than 500 participants attended yesterday's session. Thank you one and all for your valuable participation in yesterday's session. Now, I request our beloved head of the department, Dr. KVLN Acharyalu Garu, to address the gathering for today's session.
Good evening to all. I extend a warm and heartfelt welcome to today's revered resource person, Dr. TSR Murthy garu, dear esteemed faculty members and my beloved students. As we gather here on this third day of our international workshop through online, I am honored to take it as a pleasure to address the gathering of such passionate participants. Our journey over the past 2 days has been a collective endeavor to enhance our computational skills and to expand our knowledge. I want to express my appreciation to each and every one of you for your sincere participation. It is through only your presence that we have transformed this event into a good platform for enriching knowledge. By this workshop, you will get an idea on innovative computation skills and various applicable methodologies. The wealth of experience in participating in any international workshop definitely may combine with increasing enthusiasm to learn new things and exemplifying to explore the spirit of continuous improvement. Today's revered resource person is Dr. T.S.R. Murthy garu. Dr. T.S.R. Murthy garu is a source of inspiration and a treasure of knowledge in statistics. I really impressed with his simplicity, way of talking, commitment, and valuable guidance to the new generation. I have also observed a rare quality in him, that is, Sar is down to earth. He accomplished notable achievements in teaching as well as in research field. On behalf of Max Department, I am thankful to our today's revered resource person, Dr. T.S.R. Murthy garu, to accept our invitation for giving his valuable lecture in our international workshop. Thank you very much, sir. All the best to the participants. Thank you, sir.
Thank you very much, sir, for your valuable message. Today is the third day in our 1 week online international workshop. Today's speaker is Dr. T.S.R. Murthy garu, Professor, Department of Mathematics, Sri Vishnu Engineering College for Women, Bhimavaram. Now, I request one of our staff organizers, Srimati K. Nagamani, to present profound profile of Dr. T.S.R. Murthy garu.
Good evening all. Welcome you all to a 1 week online international workshop on mathematics, bridging ideas and innovations. It's my privilege to introduce today's resource person, Dr. T.S.R. Murthy garu. Dr. T.S.R. Murthy garu is a professor and head Department of Mathematics and Statistics, Sri Vishnu Engineering College for Women, Bhimavaram, AP. He did his MSc in Statistics and PhD in queuing models from Andhra University, Visakhapatnam in the year 1994 with the thesis entitled Some Waiting Line Models with Bulk Services. He published 16 research papers in national and international journals and presented 11 research papers in international conferences. He authored 3 books, 1 book chapter, and 3 are in pipeline to his credit. He has organized 5 national workshops and 1 short-term training program. He got Best Seminar Award for year 2012, Best Guest Lecturer Awards for the year 2014 and 2016 in the field of probability and statistics, and operations research from Padma Shri Dr. B.V. Raju Institute of Computer Education, affiliated to Adhikavi Nannaya University. He is a member of several academic committees and also conducted various surveys which are useful to enhance the performance of the existing systems. Dr. Murthy garu is appreciated by one and all with his best way of teaching for the last 3 decades. His contributions to the department and the college are remarkable. His helping nature, inspiring character, teaching abilities, and research capabilities are additional qualities apart from his goodness and vast experience in the field of education. Thank you all.
Thank you, Srimati Nagamani Madam, for your nice introduction about Dr. T.S.R. Murthy garu. Now, I hand over the session to Dr. T.S.R. Murthy garu. Sir, please.
Okay, sir. Thank you, sir. Thank you very much. Thank you, sir, for Acharya garu. Thank you. Very nice present, very nice opinion about me. And thank you, Sardi garu and Balay garu and Nagamani garu. Very good presentation. Thank you, sir. Thank you very much, sir. Now, I am sharing my PPT, sir.
Yes, sir. Your screen is shared, sir.
Okay, sir. Okay, sir. Okay, sir.
Yes, sir.
Okay, sir. So today's presentation is some aspects of statistical hypothesis and verification. Before start the statistical hypothesis, in real life, we often to make decisions about the population on the basis of sample information. Such decisions are called statistical decisions. First of all, we must know about the statistical decisions. After that, in attempting to arrive these decisions, which are helpful to make assumptions or guesses about the parameter, population parameter, which may or may not be true, is called the statistical assumptions and or statistical hypothesis. Before going to the starting of this presentation, there is some terminology which are helpful to understand the concept of the statistical hypothesis. In this, the terminology, the population. A population is a collection of units. Those units may be people or objects or whatever the items, the number of vehicles in the parking place. We are treated as that is also a population, or a population in your college, or in your classroom. Now, present in this workshop, the present all students are treated as a population. Whatever you are interested is knowing about, that is called the population. So population is nothing but a group of individuals under study is called a population. Here this is the population, a group of persons or the group of items or some other examples for population. This is the pens, the set of pens is treated as a population, or the penguins, we are treated as a population. A group of animals treated as a population. So population is not only people, that is we are treating a group of individuals, or the liquid also, sometimes the liquid also treated as a population, a bulk liquid or rice bag. This rice bag is treated as a population. This is the grains, this is also treated as a population. And there are two types of populations. The population size. The population size are two types. One is infinite population and finite population. And the population is denoted by capital N. The population size is denoted by capital N. So this capital N may be finite or infinite. Suppose in this population, this pen is treated as the number of pens is treated as the population. This size, the size of the population is 3 plus 3, 9 plus 12, 15, 18, 21, 22. So this is the size. This is a finite population. Whereas in this case, this is an infinite population. This is also an infinite population. This is also infinite population. This is infinite. So this is the population. Population size. This is the population and the population size. Population size is denoted by capital N. Okay. And the population constants. This is called the population constants are called the parameters. Parameters is nothing but the population related items, the related units. That is nothing but measure. The population related measure is called the parameter. The number of the average of all these population height, the height of all these people is treated as a parameter. Parameter is the related to the population constants. And the weights of this entire population, we are taking this population, the weights, the average weight of the population is called the parameter. The average height of this population is called the parameter. Parameter is nothing but the population constants. That means population mean or population standard deviation or population proportion are called the parameters. It is based on all the units of the population. So if we in this session, the number of students present in this session, we are taking the average of all the students. This entire student treated as the population. The average of all these students' height is called the parameter. If you have any doubt, please ask at any time, no problem. Okay, dear students, are you hear me? Please respond.
Sir, you are audible, sir.
Okay, sir. So that is the population constants are called the parameter. Now coming to the sample. We are already using in real life also. A sample is a finite subset of the population. Population is a lot. It is a big lot. From that big lot, we are taking a finite subset of the population is called a sample. This sample, the number of units in the sample is called the sample size. That sample size is denoted by small m. Okay, a sample is a smaller collection of units selected from the population. That means a finite subset of the population is called a sample. For example, in this is the rice bag. From this rice bag, you are taking a sample. This is a finite subset of this population. Or in this nail polish, this we are taking a samples are like this. So these are the samples. This is the population. This is the population. Okay. So the individuals in the sample, but not for those in the population. This is the population is the large bulk amount, and the sample is a small portion of the population. And now we are taking, this is the entire population. We are taking a sample. This sample is of size. How much the size of the sample? The size of the sample is 6. Number of units in the sample is called the sample size. And the number of units in the population is called the population size. The number of units in the population, that is capital N, and this is the small n. Number of units in the sample is called the sample size, that is small n. There are again two types of sample sizes are there, small samples and large samples. If the size of the sample is greater than or equal to 30, the number of units in the sample is greater than or equal to 30, then the sample is called a large sample. If the size of the sample is less than 30, that is up to 29, that is called the small sample. So this is the population. We are taking a sample. Various sampling techniques also there for selection the sample. Various sampling techniques also there. This is the population. This is the sample. And now this is the population. This is the sample. This is a spoonful of rice taking this sample. So this is the population. This is the sample. If you have any doubt at any time, please. So the statistic. The sample constants are called the statistic. The average of all these 6 members, height or weight, the average or the mean or the standard deviation or the proportion, all these are called the statistics. So sample related constants are called the statistics, and the population related constants are called the parameter. Now we want to discuss about the parameter and statistic. So our testing of hypothesis states that based on the sample information, we are expect the population. Okay. Sample constants are called the statistic, and the population constants are called the parameter. If you have any doubts, please ask me and raise your hands. So in real life, we are often make decisions about the population on the basis of the sample information. Such decisions are called the statistical decisions. So these are the statistical decisions. In attempting to arrive some statistical decisions, we make assumptions about the parameter. Such assumptions are called statistical assumptions or statistical guesses or statistical hypotheses. In this statistical decisions, in the statistical decisions, example, we may wish to determine on the basis of sample information whether a new drug is really cure the disease or not. This is the new drug. Is this drug really cure the disease? And now apply this medical to the patient. Then we are tested whether this drug is cure the disease or not. In the case of last 4 years, in our 2020, we are facing the corona. So that various drug institutes and our homeopathy or allopathy, they are really find so many drugs for curing that corona. So now, for example, in this case also, we may wish to determine on the basis of sample information whether a new drug is really effective in curing a disease. That is first example. Or in the case of quality control manager, is to determine whether a process is working properly or not, so that he can take a decision. Or the third one, a statistician has to decide whether a given coin or die is biased or unbiased. These are the statistical decisions. This is the coin, dice, and a given machine has an effective life of 20 years or not. So these are the statistical decisions. So in attempting to arrive decisions which are helpful to make assumptions or guesses about the population parameters, such assumptions are called statistical assumptions or hypothesis, statistical hypothesis. This is a very important point. In attempting to arrive decisions which are helpful to make assumptions or guesses about the population parameter. Now we want to guess about the parameter. We want to estimate the parameter. Now is it true or not? We want to estimate. That is the testing of hypothesis. So our guess is right or wrong. That is the testing of hypothesis in this one. So such assumptions are called statistical assumptions or statistical hypothesis. So statistical hypothesis is simply a statement about the parameter or the population or the nature of the population. We are expecting about the population, this is good or not. Or the average height of the people in this class is 150 centimeters. That is the, for example, this one, the population mean. That means the mean height, suppose let us assume that the population mean height is 150 centimeters, or the mean height of the population is mu equal to 150. Mean is denoted by mu. Or the weight, suppose you are taking 150 pounds or like that, the population mean. So we are assumption, we are the statistical hypothesis simply a statement about the population. So that is called the statistical hypothesis. And the other example, the average weight of students of CSC and IT branches are same in a college. Suppose you take in your college, the students average height or weight of CSC students and the average weight of IT students in your college. We assume that both are equal heights or weights. These are the CSC students. Let us assume that a group of CSC students, not 4 members, a group of CSC students are there and a group of IT students are there. Now we want to expect that the weights or the heights are equal. This is called the statistical hypothesis. This hypothesis may be true or false. So if you have any doubt, please. And suppose in your college or in our college also, 40% of the students of the college are non-vegetarian students. 40% out of 100, 40 students are non-vegetarian. So the proportion of non-vegetarians are 40 by 100. The proportion is P, that is denoted by capital P. Capital P equals 0.4. This is the assumption. We are assume that we don't know about the entire population. So we are assume that 40% of the students in our college are non-vegetarian, like that, or 50% or 60%. Whatever you expect, that is the statistical hypothesis. It may or may not be true. That is next step. And in a city, the proportion of users of homeopathy and allopathy are equal to cure a certain disease. So the users of homeopathy and allopathy in a city, we assume that they are equal to cure a certain disease. We are assume this assumption may be true or false. Whatever it may be, we assume that P1 equal to P2. The proportion, the allopathy and homeopathy are equally cure the disease. That is the proportion of users. Proportion of users is homeopathy users and the allopathy users are same, like that. All these are the examples of hypothesis. So if the statistical hypothesis completely specifies the population, then it is called a simple hypothesis, otherwise it is a composite hypothesis. Now the concept is simple and composite hypothesis. So composite, simple and composite hypothesis. Hypothesis can be split as 2 types. So many types are there, but in our testing of hypothesis, we are taking only simple and composite hypothesis. Simple hypothesis is completely specifies the parameter. Whereas composite hypothesis, it is not a specific value. It varies. It is in an interval, or it is an infinite interval, like that. So composite hypothesis and the simple hypothesis. If the statistical hypothesis completely specifies the population parameter, then it is called the simple statistical hypothesis or simple hypothesis. Otherwise, it is called the composite hypothesis. For example, if a manufacturer of a pharmaceutical product has to decide on the basis of sample whether 90% of all the patients given a new medication will recover from a certain disease. This is the pharmaceutical products. They are decide that on the basis of sample information. They are taking sample, that information, 90% of the people recover from this medicine. So in that, is that statement is true or not? Secondary. First of all, this is the statement. This is the simple statement. 90% of the patients are using this one. Is it right or wrong? That is secondary. First of all, we are taking, this is the simple hypothesis, 0.90 or P equal 0.9. This is called a simple hypothesis. Whereas in the case of second, suppose that a random variable X is a binomial with parameter with n equal 25, and we hypothesize that you already know that in the intermediate stage also binomial distribution, Poisson distribution. So that's why I put here. Here the random variable X is a binomial with parameters n, and P is there, some P, so that the mean is NP and the variance equal to NPQ binomial distribution. The P equal 0.3. P is a specific value. Here the capital P, not small p's. By mistake it printed as capital P. The parameter is always related to the population. The parameter is always related to the population. That's why it is related. It is denoted by capital letters. Whereas small p is related to the sample proportion. That is small p. But here it is wrong. It is capital P, and all these are capital P. It is just specific values are there. 0.3 or 0.5 or 0.9. Each of these are an examples of simple hypothesis. Whereas we are going to the composite hypothesis. Composite hypothesis is the statement that it is not a specific values for the parameter. That is the composite hypothesis. That population proportion lies between 0 and 0.1. This is the composite hypothesis. 0.2, 0.5. Or P is less than 0.5. Or each of these examples are composite hypothesis. So a composite hypothesis does not specify completely the values of the parameter. Parameter is always capital letters, capital P, capital A, capital B, like that. Capital letters, capital P. Okay. So composite hypothesis continued. In case of the mean, that is the proportion. This is the mean. Mu is less than 150. It may less than 150. It may be any value before 150 or greater than 150. It is not a specific value. Mu is not a, mu is equal to 150 or 75 or 60. It does not have those values. So it is greater than 150. It may be more than 150 or 151 or 150 or 170, like that. And mu is equal to lies between 0.2 and 0.8. All these are composite hypotheses. A composite hypothesis does not specify completely the values of the parameter. Now coming to the test of hypothesis. What is meant by test of hypothesis? The procedure, the test of hypothesis is a procedure which enables us to decide on the basis of sample information or sample results whether a hypothesis is true or not, is called the test of hypothesis. In the previous case, the drug inspector says that 90% of his medicine cured the disease. So now we want to test the hypothesis, that hypothesis, P equal to 90 or mu equal to 0.90 or like that. So we want to test. So test of hypothesis is the procedure which enables us to decide on the basis of sample data whether a hypothesis is true or not, whatever it may be. If it is true, we accept the hypothesis. Otherwise, we reject the hypothesis. That is called the test of hypothesis. This is the main introduction of the test of hypothesis. So in testing of hypothesis, you always begin with an assumption or hypothesis. There are two hypotheses, null hypothesis and alternative hypothesis. So these are the heart of the problem, solution of the problem. these are very important in the test of hypothesis. So first one is the null hypothesis and alternative hypothesis. Second one is the alternative hypothesis. So in testing of hypothesis, we always begin with an assumption or hypothesis. There are two types of hypothesis, null hypothesis and alternative hypothesis. Null hypothesis always states that there is no significant difference between the statistic and the parameter. Null hypothesis is always states that there is no significant difference between the statistic and the parameter, or there is no significant difference between the sample and the population. There is no significant difference between the sample and population. That means the sample is drawn from the population. You are taking a spoonful of rice. That rice taken some bag, so that there is no significant difference between the statistic and the parameter, or the sample and the population. So null hypothesis, this is the very important point. Null hypothesis always states that there is no significant difference between the statistic and parameter. Or you can write like this. Null hypothesis always states that there is no significant difference between the sample and the population. Or otherwise you say that the sample is drawn from the same population. The sample is drawn from the same population. That means sample and population, this sample is drawn from the same population. That means the population characteristics having the sample also. Sample characteristics also same. So that there is no significant difference between the sample and the population. So this null hypothesis is denoted by H naught, H suffix 0, H suffix 0, H naught. Null hypothesis. So H0 P equal to 150. H0 P equal to mu equal to 150 centimeters. That means we are assumed that the mean height of the population is 150 centimeters. We assume that the mean height of the population is 150 centimeters. Suppose in this class nearly 150 members are present in this session. Now the heights of the entire session students are treated as a population. The mean height of the entire students, whatever it may be, males or boys or girls, whatever it may be. Now I want to take the heights of the students and the mean height. I find the mean height. The mean height of this entire population is, let us assume that 150 centimeters. So this is my assumption. 150 centimeters, my assumption. Clear? Now a sample. Now we take a sample. Out of the 150, out of this 120 or 130 students, I am taking a sample of 55 or 60 members. And now calculate the sample mean, average height of the sample, and compare these two population. My assumption is mu equal to 150. My guess is 150. The average height of the students, entire student average height is 150, and I am taking a sample. Based on the sample information, I am expecting your height, average height. So in this, my expectation is average height is mu equal to 150 centimeters. Okay. And now, anybody tell me what about the alternative hypothesis? My expectation may be right or wrong. Anybody of you? Now,
sir, students are muted, sir, to avoid the disturbance.
Okay, sir.
Please carry on.
Okay, sir. Okay, sir. Now, for proportions, that is the mean. Null hypothesis always states that there is no significant difference between the statistic and parameter. We already know that. And the proportion P equal to 0.4. In the previous example, 40% of the students of a college are non-vegetarian. I expected that one. P equal 0.4. This may be true or false. This may be true or false. So this is the null hypothesis. It may be true or false. My assumption, this is null hypothesis. For the case of two means, that is single, first one is the single mean, second one is the single proportion, third one is the difference of means. In this null hypothesis always states that there is no significant difference between the parameters. There are two parameters are there because two populations or two samples are there. So that two means, so that we are estimating that there is no significant difference between the parameters related to the two populations or the two statistics, the samples. There is no significant difference between the two samples. So null hypothesis always states that mu1 equal to mu2. That means the average height or weight of students CSC and IT branches are same in a college. And my assumption is the average weights of students of CSC and IT or any other branches also are same in your college or my college. That is my assumption. That is our my null hypothesis. And the second one is the alternative hypothesis. Here, for proportion also, P1 equal to P2. For two proportions, null hypothesis always states that there is no significant difference between the two parameters or statistics. Null hypothesis, two proportions are there. In this case, the previous example, in a city, the proportion of users of homeopathy and allopathy are equal to cure a certain disease. Here, how many people, total people are there? How many people are using homeopathy and how many people are using allopathy? Now we want to find the proportion of users of homeopathy and allopathy. Now I assume that the proportion of users of homeopathy and allopathy are equal to cure the disease. That is my assumption. It may be true or false. Now the null hypothesis, that is, and the alternative hypothesis. Now what is your observation here in this picture? Do not enter, enter only. What is the meaning of this one? Do not enter or enter only. Do not enter or enter only. In this one, there are two boards are there. Don't enter. Or this is the entrance only. Of these two, any one of these statement is correct. The other is false. If do not enter is true, then enter only is false. Suppose enter only is true, do not enter is the false. These two are contradicts to each other. Like that, null hypothesis and alternative hypothesis are contradicts to each other. If one is true, the other is false, and vice versa. So that's why here I write this heading as contradiction, which is not clearly visible. Contradiction. This is the contradiction. Contradiction. So null hypothesis and alternative hypothesis are contradicts to each other. If one statement is true, null hypothesis is true, alternative hypothesis is wrong. If alternative hypothesis is true, null hypothesis is wrong. So now in the previous case, the null hypothesis, this one, is 0 P1 equal to P2. That means there is no significant difference between the users of homeopathy and allopathy. That is null hypothesis. What is the alternative hypothesis? Anybody guess it? Which contradicts the null hypothesis? This is the null hypothesis. The alternative hypothesis which contradicts the null hypothesis. The null hypothesis, alternative hypothesis may be, alternative hypothesis is denoted by H suffix 1, H1. The alternative hypothesis is denoted by H1. That may be P1 is not equal to P2. That contradicts to P1 equal to P2. Or P1 is greater than P2. Or P1 is less than P2. That is the null alternative hypothesis. There are three types of alternative hypothesis are there. Here, alternative hypothesis, it is denoted by H1. H1. Any hypothesis which contradicts the null hypothesis is called an alternative hypothesis and is denoted by H1. The two hypotheses are such that if one is true, the other is false, and vice versa. Here, in the picture, there is a controversy between these two. If this person is correct, this lady is wrong, or if she is right, she is wrong. He is wrong. Like that, there is a contradiction between these two groups. There is a contradiction between these two. So, like that, null alternative hypothesis and null hypothesis are contradicts to each other. Here, in the case of null hypothesis, here the null hypothesis is denoted by H0. Application null hypothesis is application of biofertilizer X do not increase the plant growth. Our null hypothesis is the biofertilizer X do not increase the plant growth. But we want to contradict this statement. This statement, null hypothesis and alternative hypothesis are the statements. With those two statements are contradicts to each other. So, first statement is the biofertilizer X do not increase the plant growth. That is null hypothesis. Whereas the alternative hypothesis, biofertilizer X increase the plant growth. Here, do not increase the plant growth. Here, increase the plant growth. This is the plant growth. Now, we want to test whether which statement is correct or not. We want to test by using testing of hypothesis. So, now this is a very important one, setup of null and alternative hypothesis, setup of null hypothesis and alternative hypothesis. So, if we want to test whether the population mean has a specified value, the average height of this entire class has a specified value is 150 centimeters. Now, I am taking the null hypothesis 0 mu equal to 150 mu naught and how that is called mu naught. So, here the average height of this entire group of the students is treated as 150 centimeters. That is treated as specific value mu naught. So, our null hypothesis is 0 mu equal to 150 centimeters. Against the alternative hypothesis may be, this is very important. This is the heart of the problem. Heart and art also. Setting of alternative hypothesis is an art and heart of the problem. Now, the null hypothesis states that the average height of the people is 150 centimeters or mu naught, mu equal to mu naught. Against the alternative hypothesis is H1, mu is not equal to mu naught or mu is greater than mu naught. That means the average height is more than 150 centimeters or the average height is less than 150 centimeters. Any of the three possible cases are there. So that the alternative hypothesis may be any of the three. Clear? The alternative hypothesis, any of the three. And the setting of alternative hypothesis depends on the given problem. What is the question in the problem? Then we are choosing like that, this one or this one or this one. Sometimes this is greater than or equal to mu naught or less than or equal to mu naught also. Some others treat like this one also. That is also right. This is the alternative hypothesis. And the two-tail and single-tail alternative hypothesis or two-tail test and single-tail test. So all these are the procedure of testing of hypothesis. These are the terms involved in testing of hypothesis. The alternative hypothesis H1, mu is equal to mu naught. That means the average height mu equal to 150 centimeters, not equal to 150 centimeters. That is known as two-tailed alternative or two-tailed test. That is two-tailed test. We are taking this figure, two-tailed test. This is a normal curve. The normal curve in two-tailed test. Two-tailed. This is called the left tail. This is the right tail. The right tail extended to plus infinity and the left tail extended to minus infinity. And this is the mean mu. This is a normal curve. Normal curve is a bell-shaped curve. This normal curve is a bell-shaped curve which is symmetrical about the mean mu. This is the symmetrical about the mean mu. And the shape of the curve determines the standard deviation determines the shape of this curve. There are more than some curves are there. That means skewness or liptocutic, platycutic and mesocutic. Based on the shape of the curve, we have three types of curves are there. Those are not necessary here. Here, the alternative hypothesis mu equal to mu naught is known as two-tailed alternative or two-tailed test. We are using two-tailed test. If the alternative hypothesis is of type not equal type, alternative hypothesis is of type not equal type, we are using two-tailed test. So, we want to convert the qualitative material to quantitative one. The qualitative problems converted into quantitative problems, and based on this one, we are concluding about the hypothesis. In this one, the total probability from this minus infinity to plus infinity, call it as f of x. So integral minus infinity fx dx equal to 1. Total probability, this total entire area is treated as 1. You already know in intermediate stage also some plus 2 or intermediate books, some normal distribution is also there. If you are not there, no problem. And so the alternative hypothesis is of type not equal type, then we use two-tailed test. If the alternative hypothesis of type greater than type, if the alternative hypothesis of greater than type, you use right tail test. What is right tail test? I will show the picture also. And if the alternative hypothesis is of type less than type, this is the alternative hypothesis. Alternative hypothesis may be any one of these three. If not equal type, alternative hypothesis of type not equal type, use two-tail test. Alternative type is greater than type, then use right tail test. If the alternative hypothesis is of less than type, use left tail test. So we already discussed about the two-tail test. This is the alternative hypothesis of greater than type. Greater than. Mu is greater than 150. So first, my assumption is the average height of the students is 150, but the alternative hypothesis mu is greater than 150. This is known as the right tail test or right tailed alternative. So this is the right tail. In this right tail, this is left tail. So total area is total area from minus infinity to plus infinity 1. Total area, entire total area treated as 1. This is the right tail test. Right tail test. Right tail. This one is called in future for further slides. This is the critical region. And the alternative hypothesis of type less than type. This is known as left tail test. This is the left tail test. Or left tail test or left tailed alternative. Left tailed alternative. This is the left tail alternative. This is the critical region also. Now, two-tail and single-tail test. Two-tail test is used when the alternative hypothesis of type not equal type, then we are using two-tail test. Whereas in the case of greater than or less than, we are using a single-tail test. It is right or left, whatever it may be. So the corresponding tests of hypothesis are called two-tailed or two-sided tests. Right-tailed one-sided test or left-tailed one-sided test respectively. Now, this is the important point, setting of alternative hypothesis, which depends on the problem. Alternative hypothesis. What is the question? Based on the question, we have set the alternative hypothesis. Is very important since it enables us to determine whether we have to use a single tail or two-tail test. That is very important. So based on the alternative hypothesis, we are using whether the single tail test or right tail, two-tail test. Here also, here, based on the alternative hypothesis, we are using two-tail test or single-tail test. If it is right greater than type, then use right tail test. If it is less than type, then use left tail test. Now, for example, a coin is tossed 960 times and the head turned up 183 times. Now the question is like this: is the coin unbiased? That is the question. In general, that is the question. A coin is tossed 960 times and head turned up 183 times. Is the coin unbiased? That is the question. So what is meant by unbiased? Suppose the coin is unbiased, the probability of getting head is same as the probability of getting tail. The probability of getting head is same as the probability of getting tail. For example, for easy understanding, if you are tossing the coin 100 times, we are expecting that 50 times head and 50 times tail. Or you are tossing a coin 2 times. If it is an unbiased coin, we are expecting 1 time head and 1 time tail. Clear? Suppose 10 times we are tossing an unbiased coin. We are getting 5 times head, 5 times tail. It may not be true. If it is a coin, suppose even though it is exactly an unbiased coin, suppose you are tossing 10 times the coin, tossing the 10 times a coin. First time it shows up head. The second time it may not be head or tail. It may not be head. It may be tail or head. So the first toss does not depend on the second toss. So even though it is an unbiased coin, all the 10 times shows up head. Suppose 9 times it shows up head, the 10th time maybe head or tail. Even though. So it is an unbiased coin, we are assume that, our assumption that the number of times head and the number of times tail is same. Let's assume that. That is an assumption, statistical assumption only. It is an unbiased coin. For example, in the case of cricket tossing, they are using special coins. Those are unbiased coins. They are tested, so many times tested. After testing that, they are decide that this is an unbiased coin. So that's why they are using a special box contains the coins, this type of coins. Now, one coin is given that, and this coin is tossed 960 times. Suppose we assume that, generally we assume that out of 1000 times the coin tossed, 1000 times tossed, we assume that 500 times head and 5 times tail, 500 times tail. Okay. Now, if you are understand this one, then the problem will understand. Otherwise, not possible to understand this one. So a coin is tossed 960 times and head turn up 183 times. Is the coin unbiased? So if it is 960, approximately equal to 480 times. If it is turns up head 480 times turns up head, then only it is unbiased. Approximately, let us assume that. Now test whether this coin is biased or unbiased. That is the question. Now setting up the alternative hypothesis. Null hypothesis is very important. We assume that null hypothesis always states that there is a statement in the beginning. Null hypothesis always states that there is no significant difference. That means there is no significant difference between head and tail. So that the possibility of getting head is same as the possibility of getting tail. So that the probability of getting head is same as the probability of getting tail. So that probability of getting head is half. If it is an unbiased coin, H0 equal to P equal to 0.5 means that the coin is unbiased. And against the alternative hypothesis, what is the question? Is the coin unbiased? That is the question. So we assume that in the null hypothesis, the coin is unbiased, which contradicts the null hypothesis. Then the contradiction is the coin is not unbiased. That is 0.5, not equal to 0.5. Based on the question, we are set up the null hypothesis, alternative hypothesis. Based on the question, we are set up the alternative hypothesis. Null hypothesis always states that there is no significant difference between the sample and the population, or the statistic and the parameter. So head and tail, there is no significant difference, both are equal. So the probability of getting head is half. Alternative hypothesis, the probability of getting head is not half. It may be, it is a biased coin. So whenever the alternative hypothesis is of type not equal type, then we use two-tail test. Okay. So here the setup of the null hypothesis and alternative hypothesis for a problem. And a second problem is here. A manufacturer claims that only 4% of his products are defective. Manufacturer claims that only he produced the products, and he states that one statement, that is only 4% of his products are defective. So null hypothesis always states that we are taking as 4% of his product is defective, P equal to 0.4. Null hypothesis always states that P equal to 0.4. That means the manufacturer claim is treated as true. P equal 0.4 is the manufacturer claim is treated. But what is the contradiction? What is the contradiction hypothesis? That is called the alternative hypothesis. Manufacturer claims that only 4% of his product are defectives. So that the contradiction is more than 4% of your product is defective. That is the alternative hypothesis. Clear? The alternative hypothesis P is greater than 0.4. This is the setup of alternative hypothesis. The alternative hypothesis is of greater than type. So that use right tail test. If it is less than type, then it is left tail test. Clear? And now I will explain what is the use of a right tail and what is the left tail. I will tell in future slides. Okay, right? Next one. The third example. A sample of 64 students have a mean weight of 70 kgs. Mean weight, mean. This is the mean means average. A sample of 64 students have a mean weight of 70 kgs. Can this be regarded as a sample from a population with mean weight 65 kgs and a standard deviation 25 kgs? That means, can this be regarded as a sample from a population with mean weight 65 kgs and standard deviation 25 kgs? The question is, can this be regarded as a sample from a population with mean weight 65 kgs? 65 kgs mean weight longe తీసుకున్న sample ena? This question. That is the question. A sample of 64 students have a mean weight of 70 kgs. This population weight is mean weight is 65 kg and a sample he is taking a 64 samples. Those mean weight is 70 kgs. Now, is this sample drawn from this population or not? That is the question. Now we assume that. Our assumption, we assume that. Our assumption is the sample is drawn from the same population. That means 0 mu equal to 65. 65 kg weight on the population is a sample. Question. Can this be regarded as a sample from this population? That contradicts the null hypothesis. Alternative hypothesis contradicts the null hypothesis. Alternative hypothesis contradicts the null hypothesis. Null hypothesis is mu equal to 65. Contradicts this, mu is not equal to 65. That is the when the alternative hypothesis is of type not equal type, use two-tail test. Not equal type. That's why here two-tail test. So based on the question, in the previous question, you observe that this is greater than, because a man claim only 4% of his product is defective. So we are taking 4%, but his product is maybe more than 400, 4% of defects are there. So that's why we contradict this one. But we don't take less than 0.4. If you are taking P is less than 0.4, you are indirectly support the manufacturer. Manufacturer claim only 4% of his product are defective, but you are taking P is less than 0.4 means less than, not less than 4% of his product are defective. But there is no contradiction that supports the null hypothesis. So that setting up alternative hypothesis is the art and the heart also to the given problem. And some more example for setting up alternative and null hypothesis. A lady stenographer claims that she can take dictation at the rate of 118 words per minute. Here, a lady stenographer claims that she can take dictation at the rate of 118 words per minute. So, a stenographer claims that she can take 118 words per minute. Can we reject her claim? Can we reject her claim on the basis of 100 trials in which she demonstrates a mean of 116 words per minute and a standard deviation of so and so. So 100 trials, we are taking 100 trials. In the 100 trials, she can take a mean of 116 words per minute only. Whereas she claims that she can take a dictation at the rate of 118 words per minute. She claims that she can take a dictation at the rate of 118 words per minute. But in practice, we can take 100 trials. Out of these 100 trials, she demonstrates a mean of 116 words per minute. Now, how to set up the null hypothesis and alternative hypothesis? In this, we are taking, her claim is, okay, you are taking 118 words per minute. That is the null hypothesis. Null hypothesis, that's why, that is the beauty of the null hypothesis. The beauty of the null hypothesis is there is no significant difference. The null hypothesis is taking as it is, whatever the claims. The null hypothesis is 0, mu equal to 118 words. Okay, the stenographer claim is justified here. Mu equal to 118 words. She can take 118 words per minute. But the contradiction, the alternative hypothesis, set of alternative hypothesis is mu is less than 118 words per minute. She cannot take 118 words per minute, but less than 118 words per minute. These two are contradicts to each other. If anybody doubts, please raise your hands or ask doubts also. So setup of the alternative hypothesis is very important based on the problem. Here, that's why read the problem 2 or 3 times, then set up the null hypothesis and alternative hypothesis. A lady stenographer claims that she can take a dictation at the rate of 118 words per minute. Can we reject her claim on the basis of 100 tries, in which she demonstrates a mean of 118 words per minute? So that our null hypothesis is 0. Whatever the stenographer claims, we are taking as it is 118 words. That is correct. Okay, you are taking 118 words per minute, but contradiction is less than 118 words. So the alternative hypothesis is of less than type. So use the left tail test. Now errors in sampling. What are the errors involved in the sampling techniques? In statistical hypothesis tested, then we have the following 4 cases. The following 4 cases. First one is the type 1 and type 2 errors. What is the type 1 and type 2 errors? Type 1 error is the hypothesis is true, but based on the sample information, we reject the population or hypothesis. That is the null hypothesis. The null hypothesis is true or the hypothesis is true, but based on the sample information, we reject the population. That is called the type 1 error. For example, suppose a bag contains a good quality of rice. That is, a good quality of rice bag is there. But you are taking a sample. That sample shows that some dust particles, so that immediately you reject that bag also. That is called the type 1 error. That is the type 1 error. This is also known as the producer's risk. This is also known as the producer's risk. The null hypothesis is true, but based on the sample information, we reject the hypothesis. That is called the type 1 error. This is also known as producer's risk. And the null hypothesis is false. The hypothesis is false, but it is accepted based on the sample information. That is called type 2 error. This is also called as a consumer's risk. For example, in the case of bazaar, we are going to purchase apples or some fruits. Custard apples are there. So in the upper side, big apples are there, and the lower side is small apples are there. So that we are taking a sample. So this sample, upper side sample, top side sample apples we are taking. So these are so big. So that's why we are assumed that the entire pot or entire bag is same size, same quality. So that's why you purchase the entire bag. After that, you observe that some small pots, apples also there. So the hypothesis is not correct, but you are accepted based on the sample. That is called type 2 error. After that, you are faced the problem. That's why it is called the consumer's risk. So these are the 2 errors which plays a major role in testing of hypothesis. And the hypothesis is true and it is accepted based on the sample information is called the correct decision. The hypothesis is true, and you are accepting. There is no problem, there is no error. So it is a correct decision. And the hypothesis is false and you are reject the hypothesis. That is also a correct decision. So hypothesis false, you reject the hypothesis. So that is also a correct decision. So this can be shown in a table. So reality, hypothesis is true and the hypothesis is false. Yeah, false. H0 is true or H0 is false. Or H0 is false means H1 is true. Observe this one. Test decision. So H0 is true. You are accept H0. H0 true. It is accept. Then this is the correct decision. H0 is true. You are accept H0. That is correct decision. H0 is false, you are accepting H0, that is a type 2 error. Type 2 error is the hypothesis is false, but you are accept the hypothesis, then that is called the type 2 error. And hypothesis is true, but you are reject the hypothesis, that is called the type 1 error. That is the producer's risk. The hypothesis is true, but you reject the hypothesis, that is called the type 1 error. That is the producer's risk. Suppose hypothesis is false, you reject the hypothesis, that is the correct decision. So in the previous slide can be represented in the tabular form. And one more important point is the main aim in testing of hypothesis is to reduce the errors. And note that it is more dangerous to committing of type 2 error than committing of type 1 error. The more dangerous of committing of type 2 error is more dangerous than committing of type 1 error. Type 2 error, you are committing of type 2 error is you are facing the problem. So that is the decision making. Level of significance. Level of significance means the probability of committing of type 1 error. The probability of committing of type 1 error is called the level of significance. First of all, what is meant by type 1 error? Type 1 error is the hypothesis is true, but based on the sample you reject the hypothesis. So that is called the type 1 error. So the probability of committing of type 1 error, that is called the level of significance, that is denoted by alpha. The probability of committing of type 1 error, that is probability of reject H0, reject chain. When, if it is, even though it is true, you are reject H0. That is the level of significance alpha. Alpha is the probability of committing of type 1 error, is called the level of significance. Observe this one, think of this one. This is a major role in place in the testing of hypothesis, level of significance. Committing of type 1 error. Generally, we are not committing of type 1 error. Generally, in some cases, we are committing of type 1 error. And type 2 error. Committing of probability of committing of type 2 error is denoted by beta. This is not in our syllabus. That is the power of the test. That is beta is called the power of the test. Probability of committing. So here in this case, we are using this is that term. Level of significance. Level of significance is denoted by alpha. Probability of committing of type 1 error is alpha. Setup of suitable level of significance. Generally, we are taking 5% level of significance. 5% level of significance means out of 100 cases, 5 cases only, we are rejecting only 5 cases. That means, in other words, we say that out of 100 cases, you are confident about 95% confident in your decision. So, the significance level indicates that the confidence level with which an experimenter rejects or accepts the null hypothesis. It is usually expressed as a percentage. Say 5% means that 5% equal 0.05 is the probability of reject the null hypothesis if it is true. In this, he has 95% confidence in his decision. Out of 100 cases, his decision may be right in 95 cases. And the remaining 5 cases may be wrong. His decision may be wrong. That's why that is called the level of significance. The probability of committing of type 1 error is called the level of significance. So in the 5 cases, your decision may be wrong. So the experimental decision is true, 95 cases out of 100 cases. That is 5%. And similarly, 1% also. The level of significance 1%. 1% means 0.01. So 1% means the probability of rejecting null hypothesis, if it is true, 1% out of 100 cases, your decision may be right in 99 cases. Only one case, it may be false. So you are confident about 99 cases out of 100 cases. That's why the range space is more. 99 cases, your decision may be right. So decision making is very important in this one. So setup of the null hypothesis and alternative level of significance. Setup of level of significance. Generally, if we are not asking, we are taking 5%. If we are mentioned there 1%, then you are taking 1%. Similarly, 1% means that 1% is 0.01 is the probability of rejecting null hypothesis if it is true. In this, he has 99% confidence in his decision. The experimental decision is true, 99 cases out of 100 cases. That is the 1%. And the standard normal variate Z. This is the standard normal variate Z. All these are discussed about the first stage of this one is the large samples. Large sample tests. We are taking large sample tests. Here, suppose that under a given hypothesis, the sampling distribution of the statistic is the sample constant T is approximately a normal distribution with mean, sample mean, expectation of T or expectation of theta or X bar. Mean is X bar, and standard deviation of T. SC, standard error. Standard deviation is nothing but the standard deviation of the sampling distribution of the statistic. In the regular class, we will discuss this one. The standard deviation of T is the standard error of T. Then the test statistic, we are test here, Z equal to theta minus expectation of theta by standard error of theta. This is the test statistic. దీన్నే మనం అక్కడ సాల్వ్ చేస్తాం అన్నమాట. దీన్ని బేస్ చేసుకుని మనం అక్కడ చెప్తుంటాం ప్రతిదీ. అది యాక్సెప్టా రిజెక్టా అని దీన్ని బేస్ చేసుకుంటాం. This is called the standard normal variate or Z score, and its distribution is called the standard normal distribution. Standard normal distribution with mean 0 and standard deviation 1. The standard normal distribution. The standard normal distribution. This is also a bell-shaped curve like normal distribution. In normal distribution, the mean is mu. The mean mu is symmetrical about the two sides. The mean mu. Here, standard normal distribution or standard normal curve. In standard normal curve, the mean is 0 and standard deviation is 1. Then we'll convert the normal distribution to standard normal distribution. So this is the standard normal curve having mean 0 and standard deviation 1. And now in this, the total area from minus infinity to plus infinity is total area is treated as 1. So that's why here, this is suppose this is minus infinity to plus infinity. This is 0 is there. This is the standard normal curve. The standard normal curve 0 is there. So here, this entire left part of this curve is area 0.5 and the right part of this curve is 0.5. Total 1 probability is there. So the total area under the normal curve, standard normal curve, not normal curve. This is the standard normal curve is 1. Now coming to the critical region. 1 minute. Now critical region. Critical region is the region in which the test statistic value has to fall in that region. That is the critical region. Critical region is the region in which the test statistic value falls in that region. This is the test statistic Z. This falls the region. The test statistic falls in that region. That is called the critical region. That is left tail or right tail, whatever it may be. For example, if the test statistic Z lies outside the range, minus 1.96 to plus 1.96, that is constitute the critical region or region of rejection of the hypothesis. I will explain with an example. This one. This total area from minus infinity to plus infinity, total area is 1. Total area from minus infinity to plus infinity, total area is 1. So in this 5% level of significance, we are taking level of significance 5%. This 5% is 5 by 100. That is equal to 0.05. Now you are using two-tail test. That 0.05 divided into two equal parts. The two equal parts is 0.025 and 0.025 area. 0.025 area, 0.025 area. This is. The remaining 95.95 is this one. This is the area. So in 0.025 in statistical tables also there, in that the value is, this is the value, the minus 1.96 and the plus 1.96. The area between minus 1.96 to plus 1.96 in statistical tables, there is 0.95 area. This is the acceptance region. This is the critical region. So if the test statistic, the critical region is the region in which the test statistic falls in that region. So test statistic Z lies outside the range, constitute the critical region or region of rejection, outside the range. This is minus 1.96 outside and plus 1.96 outside. This is called the rejection region, when the level of significance alpha equal to 5%. So in between minus 1.96 and plus 1.96, the total area lies between these two is 0.95. This is called the acceptance region. This is the rejection region. Red is the rejection, blue is the acceptance region. If the test statistic Z, the calculated Z value is less than 1.96, it falls in the acceptance region. If the test statistic Z more than 1.96, it falls in the critical region. Okay. This is the acceptance region. This is the critical region. In the case of 1% level of significance, 1% level of significance means we are 99% confident about our decision. So 99%. So minus 2.58 and plus 2.58, the region between minus 2.58 and plus 2.58, the area is 0.99. This is the probability. 0.99 probability is there. The remaining 1%, 1% means 1 by 100, that is 0.01. So that 0.01 is divided into two equal parts. So that's why the two equal parts 0.01 is 0.025. This is the area. This is also 0.025 area. This is the critical region. Red is the critical region. The test statistic falls if Z calculated Z value is greater than 2.58. Then greater than 2.58, the statistic Z greater than 2.58, it is false in this region, so that it falls in the critical region. So whenever it falls critical region, we reject the null hypothesis. Null hypothesis is wrong based on that. So based on this, we make decisions about the null hypothesis. Two-tailed and one-tailed tests of hypothesis. In two-tailed test, when the alternative hypothesis is not equal type, use not equal type. Then the entire critical region of area alpha lies on both sides of the right and left tails of the curve, such that the critical region of area alpha by 2 lies on the right tail and the critical region of area alpha by 2 lies on the left tail, as shown in the previous figure. If alpha equal to 5%, that means 0.05 alpha by 2, half of 5% is 0.025. So 0.025 right side critical region and 0.025 left side critical region. 0.025 left side critical region, right side critical region. So these add these two, 0.025 and 0.025. This is 0.05, and adding this one also 0.95. So the total area is equal to 1. So if we are testing a hypothesis at 5% level of significance, the size of the acceptance region on each side of the mean is 0.475, and the rejection size is 0.025 and 0.475. What is this 0.475? At the 0, this total, if you draw a line from this top to this one, the mean, the right side is half, 0.5. So that you are adding these two, that is 0.5. In left side also you are adding these two, that is 0.5. Total area is 1. Similarly, in the case of 1% also, if alpha equal to 1%, that is 0.01. Half of 1% equal to 0.025. Half of 0.025. 0.025. 0.025, it is wrong. This is wrong. 0.025. Here also 0.025. If we are adding these two, that is 0.01. And 0.01 plus 0.99. that is equal to total 1. So in this 0.025, the table value is 2.58. So minus 2.58 and plus 2.58, the area lies between these two limits. The area is 0.99. Statistical table values at 5% level of significance. If we look at the tables of areas under the normal curve, we find that the area of 0.475 corresponding to 1.96 under the standard normal standard errors. So in the statistical tables, 0.45, the table value shows that minus plus 1.96. You are in the summation value, table value summation from this one to this one, the total probability is 0.95 plus this value also. So that this entire area. Similarly, this area I want to find by using standard normal curves. Similarly, for 99%, the significance is shown above. On looking into the table areas of normal curve, we can find that an acceptance region of 0.99 is equal to 2.58. So 0.9. These are the table values for fixed table values in large sample tests only, whereas in the small sample tests, it may not be fixed. It is not fixed. It varies based on the size of the sample. So in 0.99 or 1% level of significance, the table value is 2.58. If 5%, the table value is 1.96. 5% level, the table value is 1.96. In case of two-tailed tests only and 1% level, 2.58. But right tail and left tail, there is also a table values are different. So reject the null hypothesis. Here, in case of two-tailed test, we reject the null hypothesis. If the test statistic falls in the critical region, then we reject the null hypothesis. Reject the null hypothesis means there is a significant difference between the sample and the population, or there is a significant difference between the statistic and the parameter. So that's why we reject the null hypothesis. Otherwise, we need not reject the null hypothesis. So a two-tailed test of hypothesis will reject the null hypothesis if the sample statistics is significantly different than the population parameter. Thus, the rejection region is located in both the tails. Two-tailed test, that's why the rejection region located in both the tails. Then the test falls in the critical region. Then we reject the null hypothesis. Here, mod Z. And one more important point is if the alternative hypothesis of type not equal type, the test statistic we are taking modulus, because the left tail and right tail is also there. That's why we are taking modulus of Z. We calculate the modulus of Z. That is called the test statistic. If this modulus of Z falls in the critical region, we reject the null hypothesis. Otherwise, we need not reject the null hypothesis. And if modulus of Z is greater than Z alpha means the table value. Table value is 1.96. If 5%, it is 1.96. So suppose it is calculate Z is 2 is greater than 1.96. So that this calculated Z value falls in the critical region, in this region, so that we reject the null hypothesis. We always talking about the null hypothesis only, not alternative hypothesis. We are accepting the alternative hypothesis. So we don't say that. We are talking about the null hypothesis. Null hypothesis means suppose we reject the null hypothesis, mean that implies that we accept the alternative hypothesis, but we don't say that accept the alternative hypothesis. We say that only statement about the null hypothesis only. We reject the null hypothesis or need not reject the null hypothesis. But we don't say that we accept the null hypothesis. We need not reject the null hypothesis. That means we may accept or may not accept. But that is true. Null hypothesis is true. So if mod Z is greater than Z alpha, then this Z alpha by 2, then the test statistic falls in this region, so that the test statistic falls in the critical region, so that we reject the null hypothesis. Otherwise, suppose Z is less than Z alpha by 2. That means mod Z is less than 1.96. Less than 1.96 means in this region. So that it falls in this region, so we need not reject the null hypothesis, non-rejection region. Or alternatively, we call it as, we say that it is acceptance region. Null hypothesis we are accepting. So comparison between the table value and the calculated value. If the calculated Z value is greater than the table value, we reject the null hypothesis. Otherwise, we need not reject the null hypothesis. Here we conclude that there is a significant difference between the statistic and the parameter. If we are rejecting, if you are not rejecting, there is no significant difference between the statistic and the parameter. That is the conclusion. So here, Z is less than Z alpha, then we need not reject the null hypothesis at alpha level of significance. The test Z falls in the acceptance region. So that our conclusion is there is no significant difference between the statistic and the parameter. So here 1.96, if it is less than 1.96, it falls in the acceptance region. So we need not reject the null hypothesis. Otherwise, we reject the null hypothesis. Critical region or region of rejection. Acceptance region. This is the acceptance region. Like that. The table value is minus 1.96 and this is also plus 1.96. So we are taking modulus. That's why it is 1.96. Compare with 1.96. So reject the null hypothesis if the sample statistic falls in these two regions, because it is a two-tailed test. Here we conclude that there is no significant difference between the statistic and the parameter if we are not rejecting the hypothesis. One-tailed test or single-tailed test. If the alternative hypothesis is of not equal type or greater than or less than type, then we call it as a single-tailed test. So if the alternative hypothesis is not equal type, is called a single-tailed or one-tailed test. Alternative hypothesis is greater than type or less than type. Based on the problem, we are set up this alternative hypothesis. Whatever it is greater or lesser. We have already seen some examples. For example, to test the population mean, H0 mu equal to mu naught. The null hypothesis H0 mu equal to mu naught. Against the alternative hypothesis, mu is greater than mu naught. So the alternative hypothesis is of type greater than type. So we reject the use right tail test. We use the right tail test. Whereas the alternative hypothesis is less than type, mu is less than mu naught, then we use the left tail test. In this case, the test is called a single tail test or one tail test. Based on the problem, these two are depends. This is always equal, but the alternative hypothesis greater than or less than or not equal based on the problem. We already seen some problems and the null hypothesis and alternative hypothesis also discussed. And in case of one tail test, the rejection region will be located in only one tail, either in left or in right, depending upon the alternative hypothesis. So suppose if the alternative hypothesis is of less than type, then this is the critical region. If the alternative hypothesis is of greater than type, this is the critical region. In this critical region, the table value is 1.645 for 5% level of significance. Or for 1% level of significance, the table value is 2.33. This is the 2.33. 1% probability is here. Remaining 99% probability, this is the acceptance region, this is the rejection region. So in this case, one tail test, the rejection region will be located in only one tail, either in left or right, depending on the alternative hypothesis. So suppose the right tail test is there. The alternative hypothesis H1, mu is greater than mu naught. Mu, the average height is more than 150 centimeters. Then the critical region is this one. This is the critical region, right tail test. Mu is greater than mu naught. If it is 5% level of significance, that is the table value is 1.645. If 1% level of significance, the table value is 2.33. 2.33 is here, nearby here. So now the test statistic, we calculate the test statistic. We are not taking modulus Z as it is Z and calculate Z value. If Z calculated Z value is greater than 1.645, greater than 1.645, it falls in the critical region. So that we reject the null hypothesis. Otherwise, null hypothesis means H0 reject chestam. Otherwise, we need not reject the null hypothesis. If the calculated Z value is less than 1.645, it falls in the acceptance region. So we need not reject the null hypothesis. We are accepting null hypothesis. We are treating null hypothesis is true. So based on the alternative hypothesis, we are taking either right tail or left tail or two tail test. So if the alternative hypothesis is of greater than type, use a right tail test. And the table value is different for this one. For 5% is 1.645, for 1% is 2.33. Whereas the alternative hypothesis of type less than type, we are treating the left tail test. This is called the left tail test. In this left tail test, this is 5%, this is minus 1.645. 5%, this is minus 1.645 table value. And for 1%, it is minus 2.33. Here plus 2.33, here minus 2.33 left tail. So here, this is the different case here. If the calculated Z value is less than minus 1.645, is falls in the critical region. In both the cases, right tail and the two tail test, less than is accepting. Here, less than is rejecting. If the calculated Z value is less than minus 1.645, it falls in the critical region. So that we reject the null hypothesis. Whereas if the calculated Z value is greater than the table value of Z 1.645, greater than, that's why it falls in the acceptance region. So we need not reject the null hypothesis. In case of 1% also. So when the alternative hypothesis is of greater than type, then the entire critical region of area lies on the right side tail or of the probability density curve as shown in shaded in the previous figure. In such cases, test of hypothesis is known as right tail and right tail test. Here Z is called calculated value of the statistic. So this is the right tail test. The right tail test, same as if calculated Z value is greater than the table value of Z, we reject the null hypothesis. Greater than, suppose if it is greater than 1.645, it falls in the critical region. So we reject the null hypothesis. Otherwise, we need not reject the null hypothesis. So Z greater than Z alpha, then we reject the null hypothesis at 0 at alpha level of significance. The test statistic Z falls in the critical region. Here we conclude that there is a significant difference between the statistic and the parameter. So that means the sample is not drawn from the same population. And if suppose Z is less than Z alpha, then we need not reject the null hypothesis. That means if the Z is less than 1.645, it falls in the acceptance region. Z is less than 1.645, it falls in the acceptance region. 1.645, it falls in the acceptance region. So that we need not reject the null hypothesis. If Z is greater than less than Z alpha, then we need not reject the null hypothesis at alpha level of significance. The test Z falls in the acceptance region. Hence, we conclude that there is no significant difference between the statistic and the parameter. Or we also say that there is no significant difference between the sample and the population. That is the conclusion. Now coming to the left tail test, same as the right tail test. When the alternative hypothesis is of type less than type, H1 is mu is less than mu naught, then the entire critical region of area lies on the left side tail of the probability density curve, as shown shaded in the figure, above figure. Or also again, in such case, the test hypothesis is known as a left tail or one tail test. Here Z is calculated value of the statistic. Here the left tail test. This is the left tail. The value is minus 1.645. This is the critical region. If the calculated Z value is less than minus 1.645, it falls in the critical region. So we reject the null hypothesis. Otherwise, we need not reject the null hypothesis. That means if the calculated Z value is greater than minus 1.645, it falls in the acceptance region. So that we need not reject the null hypothesis. So if the conclusion is, if Z is greater than Z alpha, then we need not reject the null hypothesis. That is the difference between the previous two cases, greater than and not equal to. This is different. In the previous case, Z is greater than Z alpha, we reject. But here we don't reject. The null hypothesis is 0 at alpha level of significance. The test statistic Z falls in the acceptance region. Hence, we conclude that there is no significant difference between the statistic and the parameter. Statistic is the sample constant and the parameter is the population constant. So, we also say that there is no significant difference between the sample and the population. If Z is less than Z alpha, then we reject the null hypothesis. There, Z is less than Z alpha, we accept there. In the two cases, greater than type and not equal type, Z is less than Z alpha, we accept there. But here, we reject the null hypothesis 0 at alpha level of significance. The test statistic Z falls in the critical region. Hence, because it less than Z alpha is Z is less than Z alpha, that means less than this one. So that's why it is falls in the critical region. So we reject the null hypothesis. Z is less than Z alpha, then we reject the null hypothesis 0 at alpha level of significance. That is, the test statistic Z falls in the critical region. Hence, we conclude that there is no significant difference between the statistic and the parameter. These are the table values, critical values using normal probability tables. From tables, so two-tailed test, Z alpha at 1% level 2.58, at 5% level 1.96, and 10% also 1.645. For right-tailed test, 1% 2.33, 5% 1.645, 10% 1.28. For left-tailed test, minus 2.33 for 1% and minus 1.645 for 5% and for 10% minus 1.28. These are the fixed table values. So compare with the table values with the calculated values. So based on, we come to conclusions. So now what is the working procedure of testing of hypothesis? Here first from the given problem, first set up the null hypothesis. That is very important. Set up the null hypothesis at 0. So based on the problem, you are set up the null hypothesis. And now come to the problem. Set up the alternative hypothesis. Null alternative hypothesis always contradicts the null hypothesis. Think of it before set up the alternative hypothesis. You think of it which contradicts the null hypothesis. So specify the nature of the test. That means specify the nature of test means it is a two-tailed test or a one-tailed test. That is the specify. Which test you are taking. So alternative hypothesis H1. And select appropriate level of significance. Level of significance alpha. If we specified 1% or 5% as it is, otherwise it is not given any hint. Level of significance we are taking generally 5% level of significance. So this generally specify in advance of the problem. After that, the test statistic Z equal to, this is the calculation part. Z equal to T minus expectation of T by standard of T. T is the statistic. This is the parameter. So theta, sometimes it is theta, expectation of theta by standard of theta, or P minus expectation of P by standard of P, or mu minus expectation of X bar, standard of X bar, like that. Problem, based on the problem, the test statistic varies. If it is a single proportion, one test statistic is there. So this is the common test statistic for all the problems. So single mean X bar minus mu by sigma by root n, test statistic. Single proportion small p minus capital P by root PQ by n. And two means X1 bar minus X2 bar by standard of X1 bar minus X2 bar. Two proportions P1 minus P2 by standard of P1 minus P2. Some formulas are there. And the conclusion, coming to the conclusion, compare the calculated Z value with the table value of Z at the given level of significance. After that, your final decision, you are accept the or reject the hypothesis. That's all.
Thank you, sir.
Any doubts, any arguments?
Sir, yes, sir. We are going to for that. Thank you, Dr. TSR Murthy Garu, for your nice lecture on some aspects of statistical hypothesis verification. This is the time for question and answer session.
Okay.
Because of the huge participants, any participant who is interested to clarify his or her doubt, please come forward to post it
Sure, sir.
in a Q&A box or chat box, which is enabled.
Okay. Okay, sir.
Sir will clarify the same. Once again, I request the participants who are interested to post their queries in Q&A box only. Sir, so far no questions are there.
Okay, sir.
Thank you one and all for your good response and valuable support. Expecting the same cooperation for the remaining sessions also. Today's session concludes with vote of thanks by staff organizer Sri I. Potraju sir.
Good evening to all. On behalf of the Department of Mathematics and the participants, I would like to express my heartfelt thanks to our today's resource person, Dr. T.S.R. Murthy sir, Professor, Department of Mathematics, Sri Vishnu Engineering College for Women, Bhimavaram, who gave such a good and informative presentation on some aspects of statistical hypothesis verification. Despite of his busy work schedule, he gladly accepted our invitation and gave a valuable talk in today's session. Hypothesis testing is a statistical analysis technique that involves testing our presumptions on a population parameter. Using sample data, it is also mainly used to evaluate an effective decision making on the given constraints of the data. By measuring and analyzing a random sample of the population, statistical analysts evaluate a valid hypothesis. At the end of a hypothesis test, the null hypothesis is either rejected or accepted, and the alternative claim is supported by sufficient evidence. Thank you very much, sir. I would like to thank our beloved head of the department and convener of this international workshop, Dr. Kevin Lacharyu sir, who guided, motivated, and supported us to do this program and encouraged us to shape out today's program. I would like to thank our principal sir and our management, Bapat Education Society, for providing us all the facilities and encouraging us to conduct this program. Without their support, it would not be possible to conduct such a program today systematically. I would also like to thank Dr. K. Mandeep Garu, Department of CSE, Institutions Innovation Council, IAC members, Sri M. Lenin Babu, Faculty of EC Department, Sri S. Prabhudas, Faculty of IT Department, Sri Srikant Nalluri, Faculty of CSE Department, Sri A. Shai Kishore, and Sri U. Venugopal, who are sincerely extending their technical support to us in conducting this international workshop. Thank you, one and all.
Thank you, sir. Thank you. And one more thing, I especially thanks for the Acharya Garu, Sardi Garu, Balay Garu, and the entire team and the management also. Thank you for giving me this opportunity. Thank you, sir. Thank you, Acharya Garu. Thank you very much. And thank you all the audience and the entire team. Thank you. Thank you very much.
Thank you, sir. Thank you very much, sir. All the students are requested to fill up the feedback link. With this, I am closing the session. Thank you, sir.
Okay, sir. Thank you, sir. If you have any students or any doubts, please contact me, sir. No problem. Thank you, sir. Thank you very much. Sir, Acharya, I am leaving, sir.
Sir, later, sir, you can leave, sir.
Okay, sir. Okay, sir. Thank you, sir. Thank you. Thank you very much. Sardi garu ఉన్నారండి?
Sardi garu కూడా లేరు, sir.
Sir. Thank you, sir. Thank you. Thank you all the team members, sir.